Imagine for a moment that our solar system doesn't just end at Pluto, that boundary we often think of as the edge. In fact, it stretches far, far beyond that, enveloped by this colossal icy sphere. It's so vast, so distant, it actually takes sunlight over 2 years just to reach its outer edges. This isn't science fiction. This is the Oort Cloud. Today, we're embarking on a deep dive into the Oort Cloud, a comprehensive exploration, and we're drawing from a really rich document that helps unveil its mysteries. Our mission really is to pull out the most important nuggets of knowledge and insight from this incredible source material. We want to help you understand this distant realm and its really profound implications. This is invisible, distant cosmic halo, but why is it so incredibly important? And what can it tell us about where we and, well, everything around us originally came from?
Okay, so let's unpack this right away. The name Oort Cloud, it kind of conjures up images of something, much more dense and visible, like clouds here on Earth. So for you, what exactly is this thing? How would you really describe its nature? And why is it considered the very, very outermost frontier of our cosmic neighborhood?
Yeah, that's a crucial distinction and honestly a pretty common misconception. When we talk about the Oort cloud, we're definitely not talking about a thick atmospheric blanket of gas or water vapor. Instead, you should picture a hypothetical, absolutely immense spherical shell, and it's incredibly sparse, made up of billions, possibly even trillions, of these primordial icy bodies. It's truly the outermost frontier of our cosmic neighborhood. It's that region where the sun's gravitational influence, though incredibly feeble out there, still just barely holds sway. These objects are really teetering on the edge, almost slipping away into the vastness of interstellar space, yet they're still, technically, gravitationally bound to our sun.
And when you say vast, my mind just immediately goes to the scale. The numbers here, they're mind-boggling. Our source material talks about it stretching from roughly 2,000 astronomical units, or AU, and for you listening, that's the distance from the Earth to the sun, all the way out to an astounding 100,000 AU. I mean, to put that in perspective, Voyager 1, our fastest outgoing spacecraft, right? It's been traveling for over 45 years, and it's still barely a blip on that scale. It's not even close to the inner edge, and sunlight taking over 2 years just to reach its outer edges. That's truly incomprehensible. How do we even start to wrap our heads around distances like that?
You're absolutely right. The sheer scale it's almost impossible to really internalize. 100,000 AAU, that's roughly 1.5 light years across. And to give you an idea of how sparse it is, imagine if the entire Oort cloud were scaled down to the size of a football stadium. Each object, even the ones a kilometer wide, would be like a tiny grain of sand. And there'd be miles, literally miles, between each grain. It's that empty. Yet within this immense, incredibly sparse volume, scientists estimate there are trillions with a T of these icy bodies. Some are just dust grains, sure, but others are larger than mountains, potentially over a kilometer in diameter.
Yeah.
And if you could somehow gather them all up and weigh them, their total mass could potentially equal several Earth masses. It suggests a really significant reservoir of material left over from the early solar system.
Wow.
It's a truly staggering amount of stuff, but it's spread so thinly across such an enormous volume that, yeah, direct observation from Earth is almost impossible right now.
Okay, so given its invisibility, its remoteness, and just its sheer, almost impossible vastness, why does this collection of icy chunks matter so much to us, down here on Earth? It sounds like it's more than just a cosmic boundary marker. The source material calls it a frozen archive and the birthplace of long-period comets. It sounds like finding a perfectly preserved vault of the original cosmic ingredients, just frozen solid in time.
Precisely. That's exactly it. Its profound importance really lies in two key aspects, and they're deeply connected to our cosmic origins. First, it is indeed the primary birthplace, the reservoir for what we call long-period comets. These are those spectacular celestial wanderers, the ones that show up in our inner solar system only rarely, sometimes only once every few millennia. They grace our skies with these dramatic appearances, tails stretching for millions of kilometers, and they originate from this distant reservoir, nudged inward by various gravitational forces. They're essentially acting as messengers, right? Delivering samples from the farthest reaches of our solar system.
Messengers, yeah, I like that.
And second, and this is arguably even more exciting for scientists, the Oort cloud functions as a frozen archive. Think about meteorites. They might have been heated during atmospheric entry or altered by impacts. Even Kuiper Belt objects, which are closer in, have undergone some evolution near the sun. But these Oort cloud objects, they've spent billions of years in the deep, deep freeze of near-interstellar space. They're largely untouched, pristine.
So completely preserved.
Pretty much. This means they could hold the molecular fingerprints of the very first chemicals that coalesced in the nebula that formed our sun. They offer an unparalleled glimpse into the raw ingredients for which our planets and potentially life itself arose. It's like finding the original untainted recipe card for the solar system, perfectly preserved in a cosmic freezer for 4.6 billion years.
That's an incredible image.
Studying these time capsules, as the source calls them, provides invaluable insights into the conditions and processes that shaped our cosmic origins. It's a direct window into the very infancy of our solar system.
It really is quite a feat, isn't it? To deduce so much about something you can't even see just from the behavior of these comets. So how do we even begin to figure out this thing exists if we can't directly observe it? It really highlights the power of observation and pattern recognition, doesn't it? Scientists started seeing patterns in comets that just didn't quite fit the models they had at the time.
Absolutely. And the concept of a distant comet reservoir didn't just pop up overnight. There wasn't a single eureka moment. It actually evolved through decades, even centuries, of careful astronomical observation and theoretical development. As far back as the 18th century, astronomers started categorizing comets based on their orbital periods, how long they took to go around the sun. And they noticed two distinct categories. There were the short-period comets, which typically completed an orbit in less than 200 years, and they generally orbited in the same plane as the planet's, what we call the ecliptic plane, the plane of Earth's orbit.
Right, kind of flat, like the solar system itself.
Exactly. But then there were the long-period comets, and these were the real enigmas. They seemed to arrive from literally all directions in the sky, with absolutely no preference for the ecliptic plane. This random orientation, coming from above, below, all angles, that was the first major clue. It strongly suggested their source had to be spherically distributed around the sun, not confined to a flat disk like the planets and most short-period comets.
Okay, so that mystery, where are these things coming from, started deepening. But then we had some pioneers who really made the connection, right? Like Ernst Öpik, and then, of course, Jan Oort, whose name ultimately got attached to the cloud.
That's right. The first really crucial theoretical contribution came from the Estonian astronomer Ernst Öpik back in 1932. He proposed that these long-period comets originated from a spherical cloud way out at the very edge of the solar system. Öpik's reasoning was quite elegant, actually. He argued that if comets were permanent members of the solar system, constantly making trips to the inner regions where they heat up and lose material, we should see far, far more active comets than we actually do. They'd burn out relatively quickly.
Ah, okay, so they couldn't be making frequent trips.
Exactly. He deduced that most comets must spend the vast majority of their existence in distant, incredibly cold regions, remaining frozen and inactive. They only become visible when some kind of gravitational perturbation occasionally nudges them into these highly eccentric, elongated orbits that bring them plunging into the inner solar system. He even correctly predicted the approximate distance of this cloud.
Wow, back in 32.
But it was Jan Oort, the Dutch astronomer, who really rigorously developed and popularized the comprehensive theory that now bears his name. In 1950, Oort published his seminal paper, The Structure of the Cloud of Comets Surrounding the Solar System and a Hypothesis Concerning Its Origin. And this wasn't just a clever guess, it was grounded in meticulous observation. It provided a coherent explanation for this long-standing cosmic puzzle. Oort carefully analyzed the orbital characteristics of 19 well-observed long-period comets. He focused on a key measurement called their semi-major axis.
Which is like their average distance from the sun over their whole orbit?
Essentially, yes. It's half of the longest diameter of their elliptical path. And he found something remarkable. For these specific comets, their semi-major axis clustered tightly around a value of 50,000 AU. It wasn't just a random scatter across all distances.
A specific distance range.
A very specific range, yeah. This strongly pointed to a particular region as their origin point. And he also confirmed, statistically, that their orbits were indeed randomly oriented in space, reinforcing that idea of a spherical, not disk-like, distribution. Oort then hypothesized that gravitational perturbations from passing stars, or maybe even the tidal forces of the Milky Way galaxy itself, occasionally nudge these distant dormant objects, just enough to send them falling into these highly elliptical orbits, bringing them into the inner solar system as the comets we observe. His calculations suggested this comet cloud extended from about 20,000 AU out to maybe 100,000 AU from the sun, with the greatest concentration right around that 50,000 AU mark he observed. This revolutionary hypothesis really laid the foundation for all subsequent Oort cloud research.
It's really quite remarkable, isn't it, how Oort's initial theory, based on just 19 comets compared to the data we have now, proved to be so prescient, so accurate in its broad strokes. So, how has our understanding of the Oort cloud evolved since that seminal 1950 paper? Have modern observations and those complex simulations you mentioned, have they confirmed his initial ideas? Or have they revealed something maybe more complex than just one big uniform bubble?
Oh, our understanding has definitely evolved dramatically since Oort's original work. Decades of additional observations studying many more comets, and especially those sophisticated computer simulations, have significantly refined and expanded our knowledge of the cloud structure and dynamics. For one thing, the modern estimates for the sheer number of objects are truly staggering. We now think the Oort cloud may contain somewhere between 1 and possibly 100 trillion objects larger than 1 kilometer in diameter.
100 trillion.
It's an almost unbelievable number, and the total mass, as I mentioned, could potentially equal several Earth masses, a huge amount of primordial stuff out there.
Okay. And structurally, is it still just one big sphere?
Well, that's where it gets more nuanced. Contemporary models now generally divide the Oort cloud into two main regions, each with slightly different characteristics and maybe even different formation histories. There's what we call the inner Oort cloud, sometimes also called the Hills cloud, named after the astronomer Jack Hills, who did important work on it. This region extends from roughly 2,000 AU out to maybe 20,000 AU. And because it's closer to the plane of the solar system, the inner Oort cloud is thought to be somewhat flattened, maybe more disk-like or torus-shaped. It probably reflects the original distribution of material closer to the solar system's plane of formation.
Okay, so not perfectly spherical there.
Right. And then beyond that, you have the outer Oort cloud, which stretches from maybe 20,000 AU out to 100,000 AU or possibly even further. This outer region is indeed thought to be much more spherical. It's had billions of years to be more thoroughly perturbed and randomized by those external gravitational influences, passing stars, galactic tides. They've had a stronger effect out there. This refined sort of two-part structure helps us explain the different types of long-period comets we observe and their varying orbital characteristics. It gives us a much more nuanced, layered view of this distant architecture than Oort originally proposed.
That's fascinating, this idea of a layered architecture. And it makes you wonder then, what are these objects, these ancient time capsules, actually made of? And what are the extreme conditions they endure out there? If these objects are like cosmic freezers preserving the primordial ingredients of creation, as you said, that implies an environment of truly extreme conditions. Can you paint a picture for us of what it's really like out there in the Oort cloud? How profoundly dark and cold is it? And how do those conditions uniquely preserve these materials for billions of years?
Yeah, it is truly an environment of incredible extremes. And you're right, those conditions are precisely what make the Oort cloud so invaluable scientifically. The objects themselves, based on what we see in comets, are believed to be primarily composed of highly volatile ices. We're talking about water ice, of course, that's a big component, but also things like frozen methane, ammonia, carbon monoxide, and carbon dioxide.
Yeah.
These are all compounds that would just be gases at the warmer temperatures we're used to.
Frozen gases, essentially.
Exactly. But critically, they also contain significant amounts of rocky material, silicates, and possibly even metallic grains mixed in with the ice. Sort of like dirty snowballs, but on a cosmic scale, and much, much older, similar to the stuff we find in meteorites and asteroids that fall to Earth. And what's truly fascinating and incredibly important if we start thinking about broader implications like astrobiology is that the icy matrix of these objects likely preserves organic compounds.
Yeah.
And we're not just talking simple molecules here. The evidence from comets suggests complex hydrocarbons, amino acids, or at least their precursors, and other prebiotic molecules.
Prebiotic meaning the building blocks for life.
Exactly. These compounds might have formed in the very early solar system, perhaps within the protoplanetary disk itself. Or some might have even originated in the vast interstellar medium before the sun even formed, and then got incorporated into these icy planetesimals as they grew. So this raises a really important question, right? If these objects are so pristine, so unchanged, what could they teach us about the very origins of life? What precise chemical ingredients were present in the primordial soup of our own solar system billions of years ago?
Wow.
The fact that they've remained in this deep freeze for so long means they've largely avoided the heating and chemical alteration that material closer to the sun would have definitely experienced.
And how are they distributed out there? Is it mostly big objects, small objects?
Good question. It seems the size distribution of objects in the Oort cloud follows what astronomers call a power law. Now, that isn't just a fancy term. It implies a specific mathematical relationship. Basically, it means there are exponentially more small objects than large ones. So if you have, say, one object of a certain large size, you'd likely have many, many more objects that are half that size and even more that are a quarter of that size, and so on, down to pebbles and dust grains.
So tons of tiny stuff for every big one.
Exactly. This specific distribution is crucial because it tells us something fundamental about how these objects originally aggregated in the early solar system, and maybe how they've been processed by collisions or gravitational interactions over billions of years. It gives us insights into the very mechanics of planet formation itself.
That really does sound like a cosmic freezer holding the blueprint for creation. And you mentioned the profound cold. Can you really quantify just how extreme those temperatures are? What does that mean for the materials out there?
Absolutely. The temperatures in the Oort cloud are just incredibly cold. They hover just a few degrees above absolute zero. Typically, we think they range from about 5 to 10 Kelvin.
Kelvin. So that's like minus 260 something Celsius, minus 400 something Fahrenheit.
That's right. We're talking about nanosheet at 263 degrees Celsius, or roughly net 450 to negative 440 degrees Fahrenheit. It's far, far colder than anything we experience naturally on Earth, even at the South Pole in winter. At these frigid temperatures, water ice doesn't behave like the ice we know. It becomes as hard as rock, it loses its typical crystalline structure, becomes amorphous, and it's incredibly brittle. Even compounds that are normally gases here, like nitrogen or oxygen, if they're present, would remain frozen solid out there.
And the sunlight.
Practically non-existent. The solar radiation at those distances is incredibly faint, something like 1/millionth the intensity of moonlight as seen from Earth. The sun, viewed from the Oort cloud, wouldn't look like a disk. It would just appear as another slightly brighter star in the sky, providing barely any illumination.
Wow, just another star.
Which makes these Oort cloud objects incredibly difficult to spot directly. They don't reflect much light, and they don't emit much heat, making them hard to distinguish from the faint glow of the cosmic microwave background radiation. It's a huge challenge for direct observation.
And the gravity out there. You said the sun's grip is weak.
Extremely weak.
Hmm.
While they are technically bound to the sun's gravity, that's what defines the edge of the solar system. That pull is so feeble at Oort cloud distances that even the smallest external perturbations can dramatically alter an object's orbit. We're talking about the gravitational influence of nearby stars as they drift past over millions of years. We're talking about the subtle but pervasive galactic tides, the differential pull of the Milky Way galaxy itself, and even the gravitational tug from massive, passing molecular clouds out in interstellar space. These external forces can easily overwhelm the sun's feeble pull at these extreme distances. They're constantly shaping and reshaping the cloud, gently nudging objects into new trajectories, and importantly, occasionally sending them on that long, slow journey towards the inner solar system where we see them as comets.
It's truly mind-boggling to think about these extreme conditions and all those subtle yet powerful forces at play. But it leads us to an even more fundamental question about this cosmic archive. If these primordial ingredients are way out there, how did they get there in the first place? The term violent birth for the cloud appears in our source material. Is that really how it happened? Did our own gas giants basically act like cosmic bullies and kick these icy building blocks out to the very edge of our solar system?
That's essentially the leading theory, yes. Violent might be a strong word, but it was certainly a very dynamic and chaotic process. The formation of the Oort cloud is intimately connected to the early, tumultuous history of our solar system, particularly the growth and migration of our giant planets, Jupiter, Saturn, Uranus, and Neptune. Current models strongly suggest that the objects now residing way out in the Oort cloud didn't actually form at their current locations. It's too far from the sun, too little material out there initially. Instead, most of them likely started life as icy planetesimals. These are the fundamental building blocks of planets and moons, and they were born much closer to the sun. Probably in the colder outer regions of the protoplanetary disk, maybe in the region between the orbits of what are now Jupiter and Neptune.
So where the gas giants are now, roughly.
Roughly in that zone, yes. During the solar system's first few 100 million years, the region beyond the orbit of where Mars is now, out past Jupiter and Saturn, was a really chaotic and densely populated environment. It was filled with countless icy planetesimals, small ones, big ones. Now, as Jupiter, Saturn, Uranus, and Neptune grew to their current immense sizes by gobbling up gas and dust, their powerful gravitational fields acted like giant cosmic slingshots.
Slingshots, okay.
They gravitationally scattered these smaller icy bodies in all directions. Computer simulations show this very clearly. The vast majority of these planetesimals were probably either ejected from the solar system entirely, becoming interstellar wanderers lost between the stars.
Wow, ejected completely.
Or they were flung into these highly eccentric, very elongated orbits that carried them out of the distant reaches where they now reside, forming the Oort cloud. So yes, In a way, the immense gravitational might of our own gas giants was the primary architect of this distant reservoir. They effectively kicked a fraction of these building blocks out to the edges through this process we call planetary scattering.
So it was like a massive cosmic game of billiards or maybe pinball, and these objects were the balls being scattered everywhere. And this ties into some of the more modern theories about our solar system's early dynamics, doesn't it? Like the grand tack model and the nice model. These aren't just abstract ideas, they describe specific, pretty dramatic events in our solar system's past, right?
Absolutely. These modern refinements, these models, provide incredibly detailed scenarios for how that scattering process might have happened,
Yep.
integrating our understanding of how planets don't just sit still, they can migrate, they can move around, especially early on. The Grand Tack model, for instance, proposes a really dramatic early history specifically for Jupiter. It suggests that Jupiter didn't just form and stay put, it actually migrated inward toward the Sun first, maybe getting as close as 1.5 AU, that's closer than Mars is now.
Jupiter moving in. That's
Mm.
wild.
It is. And then, due to interactions with Saturn, it reversed course and migrated back outward towards its current position. This inward then outward tack, like a sailboat changing direction, would have gravitationally scattered immense amounts of material in its wake, both kicking stuff inward towards the terrestrial planets and flinging stuff outward. The outward scattering of icy planetesimals, particularly as Jupiter moved back out, would have played a really significant role in populating what would eventually become both the inner and the outer parts of the Oort cloud.
Okay, that's the grand tack. What about the nice model?
The Nice model, named after the city in France where it was developed, describes a slightly later period, maybe several 100 million years after the solar system's formation. It focuses on a period of orbital instability among all the giant planets. It proposes that the giant planets Jupiter, Saturn, Uranus, Neptune initially formed in a much more compact configuration than they are in today, closer together and maybe closer to the Sun.
Tighter orbits.
Exactly. And over time, subtle gravitational interactions between the planets themselves, and particularly interactions with a massive outer disk of leftover planetesimals, caused their orbits to become unstable. This led to a dramatic and relatively rapid rearrangement. Jupiter might have moved slightly inward, while Saturn, Uranus, and especially Neptune migrated significantly outward. As Neptune plowed outwards through that disk of icy bodies, it scattered hundreds of millions, maybe billions, of objects throughout the outer solar system.
Like a snowplow effect.
Kind of, yeah. Many of these scattered objects, primarily originating from what we now think of as the Kuiper Belt region, or just beyond, would have also been flung out to Oort Cloud distances, adding to its population. What's truly fascinating here, as you said, is how interconnected everything is. The evolution of our inner solar system, the final positions of the giant planets, it's all tied up with the formation of this incredibly distant reservoir. It really is a grand cosmic dance where the dramatic early actions of the planets directly influence the creation of our most distant frontier, shaping its very structure and population.
That really brings it home, doesn't it? How everything in the solar system, from Mercury way out to the Oort cloud, is linked through this shared history. So if it had such a dynamic birth, is it just sitting there quietly now? Or is it still an active, ever-changing environment constantly being sculpted by cosmic forces, even billions of years later?
Oh, it's definitely not static. The Oort cloud continues to evolve even today, although perhaps at a much slower, more subtle pace than during its tumultuous formation period. One of the most significant ongoing external influences comes from what we call galactic tides. This is the differential gravitational pull from the Milky Way galaxy itself. As our solar system orbits the galactic center, the galaxy's gravity doesn't pull uniformly on the whole Oort cloud.
It stretches it.
It kind of gently squeezes and stretches it, yeah. This happens periodically over timescales of tens of millions of years. These tidal effects, this subtle squeezing and pulling, can slightly alter the orbits of Oort cloud objects. They can gradually nudge some of them out of their stable, distant orbits and into new trajectories that bring them closer to the inner solar system. Eventually, these nudged objects manifest as the long-period comets we see. Some researchers have even suggested a potential, though it's still debated, link between peaks in these galactic tide-induced comet showers and some of the mass extinction events we see in Earth's geological record, maybe recurring roughly every 35 to 40 million years.
Wow, a galactic rhythm potentially affecting life on Earth.
Potentially, yeah. It's an intriguing idea. Passing stars also play a crucial, perhaps even more direct role in the cloud's ongoing evolution, especially for triggering individual comets. On average, calculations suggest a star passes within about 10,000 AU of our Sun, well within the outer Oort cloud every few million years. And these stellar encounters, even from what seems like a huge distance, can profoundly perturb the orbits of Oort cloud objects due to the sun's weak grip out there. Computer simulations suggest that these relatively frequent stellar encounters are actually responsible for the vast majority of the new long-period comets that actually enter the inner solar system for the first time, perhaps more so than the slower, more gradual effect of galactic tides for individual comet events.
Is there an example, like a star heading our way?
There is. A particularly relevant example is the red dwarf star Gliese 710. Based on its current trajectory, astronomers predict that this star will pass remarkably close to our Sun, within about 1,300 AU in approximately 1.35 million years.
1,300 AU, that's inside the inner Oort cloud.
Exactly. It's predicted to plow right through the inner cloud. When it does, its gravitational influence will significantly perturb the Oort cloud, potentially dislodging a huge number of objects and sending a noticeable surge of comets towards the inner solar system. This effect would likely play out over a period of millions of years following the encounter.
Something for future generations to look out for.
Indeed. And finally, even closer to home, the outer giant planets, particularly Jupiter with its immense gravity, continue to act as a kind of gravitational shepherd, or maybe a gatekeeper for comets that do manage to get nudged inwards and enter the inner solar system. These planets can interact with incoming comets. They can either eject them from the solar system entirely, sending them on truly interstellar trajectories, never to return. Or they can capture them into shorter period orbits, sometimes trapping them within the Kuiper Belt region or even closer. This processing by the giant planets can explain how we get comets with intermediate orbital periods, say ranging from 20 to 200 years, like Halley's Comet. They don't quite fit the long-period Oort cloud or short-period Kuiper Belt categories neatly. They might be captured Oort cloud objects.
So it really is a profoundly dynamic and ever-changing frontier, constantly being sculpted by these immense galactic forces, passing stars, and even our own planets, right up to today.
Okay, so we've established that the Oort cloud is incredibly distant, incredibly sparse, and remains largely unseen directly. It really raises a fundamental question for us. How certain are we that these comets, these fleeting visitors we do see, truly come from there? What's the definitive evidence linking them to this invisible cloud?
That's a critical question, absolutely. And our certainty is built on a really solid bedrock of strong observational evidence, even without having direct images of the cloud itself. The primary line of evidence comes from the things we can observe and study in great detail, the long-period comets themselves. These comets are distinguished by several key characteristics that, when taken together, strongly support the Oort cloud theory. First, their orbital periods. They typically exceed 200 years, and often they take thousands, tens of thousands, or even millions of years to complete just a single orbit around the sun. Some comets we see might be on their very first trip inwards. Millions of years for one orbit.
It's mind-boggling. Second, their orbits are highly eccentric. That means they follow extremely elongated elliptical paths. These paths carry them from the immediate vicinity of the sun, where they become active and visible, way, way out to distances far beyond Pluto, stretching deep into the proposed Oort cloud region. Their farthest point, their aphelion, is often calculated to be tens of thousands of AU away.
So the orbits point back to that region.
Exactly. But perhaps the most crucial piece of evidence is their arrival direction. Unlike the planets, or the short-period comets, which mostly orbit in that relatively flat plane, the ecliptic, long-period comets come at us from literally all directions in space, above the plane, below the plane, every angle in between. This random isotropic distribution is perfectly consistent with their origin being in a vast spherical shell surrounding the solar system, rather than a flattened disk like the Kuiper Belt.
That makes sense. A sphere would look random from the inside.
Precisely. And furthermore, when astronomers meticulously analyze their orbital data, particularly calculating those semi-major axes we talked about, they find that many, many long-period comets have semi-major axes clustering specifically around 20,000 to 50,000 AU. This statistical clustering isn't random. It strongly supports the Oort cloud model and lines up beautifully with OPIC's and especially Oort's original hypotheses. It provides compelling evidence for specific distant reservoirs of their primary birthplace.
That's incredibly compelling, yeah. We can infer so much about an unseen structure just by tracking the paths of its outgoing messengers, as you called them. But are there other lines of evidence, anything else that corroborates this, or is it really all just based on those comet trajectories?
No, it's definitely not just the trajectories, although those are fundamental. There are several other powerful lines of corroborating evidence that significantly reinforce the Oort cloud theory. Stellar perturbation studies are a big one. Astronomers have conducted extensive research looking into how passing stars should affect the Oort cloud over time. By precisely tracking the past motions and predicting the future motions of nearby stars through our galaxy, researchers can identify specific close stellar encounters that should have gravitationally disturbed the Oort cloud and potentially triggered comet showers in the past.
Like checking if a star pass corresponds to more comets later.
Exactly. And studies have found statistically significant correlations between these predicted close stellar encounters in the past few million years and observed increases, or peaks, in the number of long-period comets entering the inner solar system during certain subsequent periods. Now, the correlations aren't always perfect, partly because comet orbital periods are so incredibly long, the effects of an ancient stellar encounter might still be playing out, spread over millions of years. But they do provide substantial additional support for the Oort cloud hypothesis. It effectively shows evidence of that push from outside forces perturbing the cloud.
Okay, so the physics of passing stars matches the comet record. What else?
We also have crucial chemical and isotopic evidence, which comes from analyzing the light from the comets themselves and sometimes even collecting dust particles. The chemical composition of long-period comets, the specific types of ices and organic molecules they contain, powerfully supports their origin in the Oort cloud. This composition is entirely consistent with formation in the extremely cold outer regions of the early solar system, far from the sun's heat, where all these volatile compounds could remain frozen and preserved for billions of years.
A frozen archive idea again?
Exactly. For example, measuring the ratio of deuterium, heavy hydrogen, to regular hydrogen in the water ice found in comets gives us a kind of chemical fingerprint. For many long-period comets, these deuterium to hydrogen, or DH, ratios align well with what we'd expect from material formed in those very cold outer solar system conditions. It's different from the ratios typically found closer to the sun.
So it's like cosmic forensic science then. The comets themselves carry the chemical evidence of their birthplace right to our doorstep, helping us understand its pristine nature.
That's a great way to put it, yes. Their chemistry tells a story about where they've been and how little they've changed.
And what happens when one of these icy messengers actually makes that incredibly long and presumably fiery journey inward towards the sun? What secrets do they truly reveal as they get closer and light up, becoming visible to us? It must be a pretty dramatic transformation from a dark ice chunk.
It is indeed a dramatic and, for scientists, an incredibly valuable transformation. When an Oort cloud object, which is essentially a dark, inert, frozen chunk of ice and dust, begins its long fall towards the inner solar system, it starts to warm up as it gets closer to the sun. This warming typically becomes significant when it's roughly 3 to 5 AU from the sun, so still way out beyond the orbit of Mars, somewhere between Jupiter and the asteroid belt. At these distances, the solar heating becomes intense enough to cause its most volatile ices, things like frozen carbon monoxide, carbon dioxide, maybe methane, to sublimate. That means they turn directly from a solid into a gas, bypassing the liquid phase entirely because the pressure is so low in space. This process is called outgassing.
So the ice just turns straight into gas.
Right. And as these volatile compounds turn into gas, they escape from the comet's solid nucleus, and they drag tiny dust particles along with them. This escaping gas and dust creates a tenuous, glowing atmosphere around the nucleus, which we call the coma. It can grow to be enormous, sometimes larger than Jupiter. As the comet continues its approach closer to the sun, the solar wind, that constant stream of charged particles blowing out from the sun, and also the pressure from sunlight itself, push these gases and dust away from the coma. This forms the characteristic tails, usually a brighter, curved dust tail and a fainter, straight ion, or gas tail, that can stretch for millions, even hundreds of millions of kilometers across space.
And that's what we see, the coma and the tail, and not the tiny nucleus itself, usually.
Exactly. And this spectacle isn't just beautiful. It's, as you said earlier, a direct spectroscopic sample of pristine material from 4.6 billion years ago, delivered right to us.
So what can we learn from analyzing that light, that coma and tail?
A huge amount. The behavior and activity of these long-period comets provide crucial, direct insights into the Oort cloud's conditions and its original composition. Because these objects have spent almost their entire existence in that deep freeze, they preserve pristine samples of early solar system material, almost untouched by the processes that have altered inner solar system bodies, like asteroids or even planets. Spectroscopic observations, basically analyzing the wavelengths of light emitted or absorbed by the coma and tail, allow us to identify the specific molecules present. We've confirmed not only water, carbon monoxide, methane, and ammonia, but also a whole zoo of more complex organic compounds. We've detected things like methanol, formaldehyde, hydrogen cyanide, and even amino acid precursors like glycine, or at least their building blocks. In the material coming off comets,
Amino acids.
or their precursors, yes, which is incredibly exciting from an astrobiology perspective. The relative amounts, the ratios of these different compounds provide incredibly detailed information about the temperature and the chemical conditions in the specific region of the early solar system where these objects first formed. Even the dust particles released by active comets carry important information. Analysis of dust particles collected directly from comets by spacecraft, like NASA's Stardust mission to Comet Wild 2, though that was a shorter period comet, likely from the Kuiper Belt originally, shows fascinating details. Some particles show evidence of having been heated and altered by shock waves or high temperatures very early in the solar system, suggesting mixing of materials from different regions. While other particles appear completely pristine, like tiny time capsules, a testament to their long, cold slumber out in the Oort Cloud or Kuiper Belt.
That's just astounding. So these fleeting cosmic visitors are basically flying laboratories, delivering samples of primordial material right into our observational reach. Have there been any particularly famous visitors, specific comets that really helped us learn a lot about the Oort cloud? What specific secrets did they reveal?
Oh, absolutely. Several spectacular long-period comets have provided treasure troves of data about the Oort cloud, thanks to intensive study campaigns using our best ground-based and space-based instruments. Comet Hale-Bopp, which was discovered in 1995, was truly a gift to astronomers. It was one of the brightest comets of the 20th century, easily visible to the naked eye for a remarkable 18 months. That's an extraordinarily long time for a comet to remain so bright and active.
18 months, wow.
Yeah, it was incredible. Its enormous estimated size, somewhere between 40 and 60 kilometers in diameter for the nucleus, meant it was unusually active and released vast amounts of gas and dust. This allowed for incredibly detailed spectroscopic observations over a long period. Those observations provided unprecedented insights into Oort cloud composition. They revealed not just the expected water and common volatiles like carbon monoxide, but also a rich diversity of other molecules, including some complex organic species like hydrogen cyanide, HCCN, and isocyanic acid, HNCO, in much higher abundances than had been typically seen before. This really suggested a very rich chemical inventory was available in the outer parts of the early solar system, and these complex molecules are crucial for understanding potential pathways to prebiotic chemistry.
So Hale-Bopp showed us the chemical richness. Any others?
Another really famous visitor was Comet Hyakutake, discovered just a year later in 1996. Hyakutake was much smaller than Hale-Bopp, but it passed unusually close to Earth, just 15 million kilometers away, which is quite close in cosmic terms. This close pass offered a unique opportunity for detailed study. Researchers were able to detect X-rays emanating from Hyakutake's coma, which was a surprising discovery at the time. It indicated complex interactions happening between the highly charged particles in the solar wind and the neutral gases escaping from the comet's nucleus. Detailed study of Hyakutake also revealed complex organic molecules, similar to Hale-Bopp, and it provided some of the best early measurements of isotopic ratios in comet water, specifically its deuterium to hydrogen DH ratio. That ratio offered crucial data points for the ongoing debate about whether comets like those from the Oort cloud could have delivered a significant fraction of Earth's oceans. It also gave us insights into how comets interact with Earth's own magnetosphere when they pass close by.
So each comet adds a piece to the puzzle.
Exactly.
Yeah.
And more recent visitors, like Comet Ison back in 2013, which unfortunately disintegrated as it passed the sun, and Comet Lovejoy in 2014, have also been studied intensively with increasingly powerful modern instruments. These instruments can detect ever more trace compounds, fainter molecules, and they can map the three-dimensional structure and velocity fields within cometary comas and tails with incredible precision. This continuously refines our understanding of Oort cloud composition, structure, and the processes that drive cometary activity. Each one is truly a unique, invaluable window into this distant, unseen realm.
Okay, so we can't directly see the Oort cloud itself, at least not easily, but we're getting a lot of really compelling indirect evidence and increasingly detailed chemical information through these comet messengers. So how are scientists currently trying to peer into this unseen frontier? You mentioned computer simulations earlier. Are supercomputers essentially letting us see what our telescopes can't directly image yet?
Yes, to a very significant extent, supercomputers have become arguably our most powerful tool for exploring the Oort cloud's deeper mysteries. Modern research in this area relies heavily on incredibly sophisticated computer simulations. These models have to incorporate the complex gravitational interactions operating over billions of years involving the sun, all the planets, especially the giants, the cumulative effects of nearby passing stars, and those subtle but persistent galactic tides from the Milky Way. All these forces have to be calculated simultaneously to simulate how the Oort cloud likely formed, how it evolved over cosmic time, and how it continues to be shaped today.
That sounds computationally intense.
Oh, incredibly. These models track the orbital evolution of millions, sometimes even billions, of individual virtual Oort cloud objects, starting from their presumed formation locations in the early solar system disk, simulating their scattering outwards, and following their paths and interactions right up to the present day. Recent advances in computational power, faster processors, better algorithms, have allowed astronomers to run increasingly detailed and realistic simulations. They can include vast numbers of individual test particles representing the Oort cloud objects and model the complex gravitational dynamics with higher fidelity than ever before. These simulations provide crucial insights into the cloud's likely overall structure, confirming that flattened inner region and spherical outer region idea. They help us estimate its total mass and predict the rate at which it should supply comets to the inner solar system, which we can then compare to observations.
So they test the theories against what we see.
Exactly. And one significant finding from recent, more powerful simulations, as we touched on earlier, is that the Oort cloud likely has an even more complex internal structure than we used to think. Rather than just a simple two-part shell, the simulations suggest the cloud might have distinct subregions, streams, or clumps with different properties and perhaps slightly different evolutionary histories, maybe related to specific scattering events or resonances in the past.
Wow.
So yes, in a very real sense, these supercomputers are letting us see and understand the large-scale structure and the intricate dynamics of this vast unseen structure in ways that direct observation simply cannot achieve yet. They allow us to test hypotheses about its formation and evolution over the entire age of the solar system.
That's an amazing use of technology, really, to fill in the gaps where direct observation is currently impossible. But speaking of observation, are there advances happening in observational techniques themselves that might bring us closer to actually seeing some of these distant objects directly? Or maybe getting even more detailed information from the comets they send our way? How close are we realistically to maybe finally getting a direct photo of an Oort cloud object out there in its natural habitat?
We are indeed getting closer, bit by bit, but it remains an immense and ongoing challenge. Direct optical observation of individual Oort cloud objects in their natural inactive state, just sitting out there cold and dark, is still pretty much beyond our current capabilities. They're just too small, too far away, and reflect virtually no sunlight.
Still too faint, too far.
Right. However, advances in observational techniques are continuing to provide new insights into their properties, both directly and indirectly. Infrared surveys, especially those conducted by space-based telescopes, which get above Earth's obscuring atmosphere, have been key. Missions like IRAS back in the 80s, WISE more recently, and the Spitzer Space Telescope have significantly pushed the detection limits for cold, faint objects in the outer solar system. Now, while these missions haven't directly imaged dormant Oort cloud objects, they're still too faint, even for Spitzer or WISE. They've done a fantastic job of characterizing the population of the much closer and slightly brighter Kuiper Belt objects beyond Neptune. And understanding the KBO population gives us important clues about the broader distribution and nature of icy bodies throughout the outer solar system, including those that likely ended up in the Oort cloud.
So studying the Kuiper Belt helps understand the Oort cloud.
It provides context, exactly. Meanwhile, the study of the active long-period comets, our messengers, is becoming increasingly sophisticated. As we discussed, new instruments on ground-based telescopes and in space are capable of detecting ever more trace compounds, measuring isotopic ratios with higher precision, and mapping the detailed three-dimensional structure and gas flows within cometary comas and tails. These observations give us ever more precise information about the chemical composition and physical properties of the Oort cloud objects before they came inwards. Radio astronomy has also emerged as another really important tool. Powerful radio telescopes can detect faint molecular emission lines, specific frequencies of radio waves emitted by different molecules coming from the gases in cometary atmospheres. This provides incredibly detailed information about their chemical composition and the complex chemical reactions happening as they become active near the sun.
What about future telescopes? Anything specific coming online?
Yes, there's a lot of excitement about future prospects. The James Webb Space Telescope, JWST, with its unprecedented infrared sensitivity and incredible angular resolution, theoretically could have a shot at detecting the faint thermal emission, the heat signature, from some of the very largest Oort cloud objects directly, even if they're inactive. This would require extremely long exposure times, perfect conditions, and knowing exactly where to look, so it remains an ambitious, maybe borderline target. but the capability might be there.
A possibility, though.
A possibility. And perhaps even more significantly for Oort cloud science, there's the Virasey-Rubin Observatory, VRO, formerly known as LSST. This next-generation ground-based survey telescope is scheduled to begin full operations in the next couple of years. VRO, with its huge 8.4-meter primary mirror and incredibly wide field of view, will repeatedly monitor the entire southern sky every few nights, specifically searching for faint, moving objects. It's expected to detect potentially hundreds, maybe thousands, of faint objects with orbits that place them in the inner regions of the Oort cloud, the Hills cloud bodies, that are perhaps just beginning their journey inwards.
So VRO could actually map out the inner cloud population.
It could give us the first real statistical census of the inner Oort cloud population, yes, providing unprecedented data on their distribution, their orbits, maybe even hints of their sizes and colors, which relate to composition. So, while a direct photo of a truly distant, dormant Oort cloud object way out at 50,000 AU is still extremely difficult, these new tools significantly improve our chances of detecting objects closer in, maybe down to a few thousand AU, and understanding their properties much better, either directly or through their subtle gravitational effects on other bodies, or just by finding more of them.
That's incredibly exciting to think about what VRO and maybe even Webb might reveal in the coming years. And this leads us nicely into some really fascinating interdisciplinary connections you touched on earlier. This distant icy cloud isn't just about rocks and ice way out in space. It could hold clues about how life started right here on Earth and maybe even influence our planet's long-term climate. That's truly mind-blowing when you think about it.
It genuinely is. And modern Oort cloud research is increasingly revealing these profound connections to broader scientific fields, showing how interconnected everything is. In planetary science, for instance, recent discoveries based on observations of dusty debris disks around other stars strongly suggest that comet clouds, analogous to our own Oort cloud, are likely common features of planetary systems throughout the galaxy. Finding these exoort clouds provides crucial comparative context for understanding our own solar system structure and formation.
So we're not necessarily unique in having one.
Probably not. By studying our Oort cloud, we gain insights into the processes of planet formation and scattering that might be fairly universal. It helps us understand whether our solar system has any unusual characteristics, perhaps related to the specific masses or migrations of our giant planets, that might make it particularly well-suited for the development of life. This helps us assess the potential prevalence of Earth-like planets and habitable environments elsewhere in the universe.
Okay, so planetary science context. What about astrobiology, the life question?
Right, astrobiology. Here, the Oort cloud is increasingly highlighted as this potential vast reservoir of primordial organic compounds, and maybe even though this is highly speculative, a place where primitive life or its precursors could be preserved for billions of years. It's fascinating for future study because, as we've said, these objects preserve complex organic molecules, maybe even things like amino acids formed in the early solar system or interstellar space, shielded from harsh radiation and heat in that deep freeze. Computer models suggest that during the late heavy bombardment period, roughly 3.8 to 4.1 billion years ago, a significant number of comets, likely originating from both the Oort cloud and the closer Kuiper belt scattered disk, struck the inner planets, including early Earth. These impacts could have delivered substantial amounts of water and crucial organic material to the young Earth.
Delivering the ingredients for life.
Potentially, yes. The isotopic composition of water in long-period comets, specifically that deuterium to hydrogen, diatio we mentioned, provides crucial clues about whether comets could have been a major source of Earth's oceans. The picture there is a bit complicated. Early measurements, like from Halley and Hale-Bopp, suggested that many comet DH ratios were too high, about double Earth's ocean-water ratio. But more recent observations of some comets, including Comet 67P Churyumov-Gerasimenko, visited by the Rosetta mission, again likely a Kuiper belt object originally, have shown DH ratios much closer to terrestrial values, or even lower. So the jury is still out, but it keeps alive the possibility that comets contributed significantly to Earth's water inventory.
So the water story is complex. What about the organics?
The Oort cloud could certainly contain a rich inventory of those organic compounds like the amino acid glycine, detected indirectly, and the complex hydrocarbons found in cometary dust. These could absolutely have provided some of the raw materials, the building blocks, needed for the origin of life on Earth. And then there's the even more speculative idea known as panspermia, the idea that life itself, or at least its complex precursors, could be transported between planetary systems, maybe shielded inside comets or asteroids. Could Oort cloud objects preserve and transport biological materials across vast distances of space and time? It remains an intriguing, though unproven possibility that future missions capable of analyzing pristine cometary material might one day investigate.
Panspermia.
Well,
Okay, and finally, the climate science connection.
yes, there are compelling connections to long-term climate science as well. Studies looking at how major comet impacts might have affected Earth's climate in the past, perhaps triggering global cooling events or delivering large amounts of volatiles like water vapor and carbon dioxide to the atmosphere are important. Understanding the flux, the rate, and timing of comet bombardment from the Oort cloud over geological timescales is crucial for understanding these potential long-term influences on Earth's atmosphere, oceans, and overall habitability. The Oort cloud isn't just a static museum. Its dynamic evolution, driven by galactic tides and passing stars, directly influences the impact environment in the inner solar system, and thus potentially shapes Earth's long-term climate history.
So, yeah, definitely far more than just rocks in space. It's a key piece in the puzzle of planets, life, and even our own planet's history. Okay, so if the Oort cloud holds such incredible secrets, maybe even clues to life's origins, what would it actually take to go there, to directly explore this ultimate frontier? Our source material rightly refers to it as the ultimate distance challenge. I mean, we said the inner edge is roughly 2,000 AU, about 100 times farther from the sun than Pluto. What kind of travel times are we even talking about with current technology just to get to its nearest doorstep?
Yeah, the primary obstacle, as you've absolutely highlighted, is simply the unfathomable distance. 2,000 AU for the inner edge is just immense. And the main cloud, the outer part, extends out to 100,000 AU or more. With our current spacecraft, propulsion technology, chemical rockets, maybe some gravity assists within the solar system, reaching even the inner edge of the Oort cloud would literally take thousands of years.
Thousands, not hundreds.
Thousands. For context, Voyager 1, which is our fastest and most distant outgoing spacecraft, has been traveling for over 45 years now, and it's only just reached about 163 AU from the sun. That's an incredible achievement, a huge distance, but it's still less than 1/10 of the way to the inner edge of the Oort cloud. Voyager 1 is traveling at about 17 kilometers per second relative to the sun. At that speed, it would still take well over 300 years just to reach the 2,000 AU mark, the very closest edge of the Oort cloud. And it would take tens of thousands of years to actually traverse the main part of the cloud.
Okay, wow, 300 years just to get there.
So yeah, it truly highlights how incredibly immense interstellar space, even the outer reaches of our own solar system, really is. The technological leaps needed to seriously contemplate venturing into these frontiers for dedicated missions are monumental. We're talking orders of magnitude improvement over current capabilities.
Thousands of years is definitely not a quick trip to the cosmic store, is it? So we really were talking about technologies that sound straight out of science fiction just to even consider sending a probe there within a human lifetime or even several lifetimes. What kind of revolutionary propulsion technologies would we actually need? And, what's the closest thing we might have now, conceptually at least, that could make even a small dent in those daunting travel times?
To make any kind of meaningful progress on those travel times, to reduce them from millennia down to, say, centuries or maybe even decades for a flyby mission, we would indeed need truly revolutionary propulsion technologies. We're talking about concepts that are currently mostly in the realm of theoretical development or very early-stage laboratory research. For example, there's a concept of nuclear pulse propulsion, famously explored by Project Orion back in the 50s and 60s. This would involve detonating small, controlled nuclear explosions behind a spacecraft, using a pusher plate to absorb the impulse and generate thrust. Theoretically, it could achieve speeds orders of magnitude greater than chemical rockets.
Using nukes to push a ship.
Essentially, yes. It has obvious challenges, but the physics is sound. Similarly, fusion rockets, which promise far higher specific impulses, meaning much greater fuel efficiency by harnessing the energy released from controlled nuclear fusion, are another long-term possibility. If we could build a compact, efficient fusion reactor, it could enable much faster interplanetary and potentially interstellar travel. Then there are even more exotic concepts like beamed energy propulsion. This could involve using vast, incredibly thin solar sails, maybe kilometers across, pushed not by sunlight, but by powerful laser beams originating from a massive array deployed perhaps near Earth or the sun.
Lasers pushing sails.
Exactly. Projects like Breakthrough Starshot are exploring this concept for sending tiny probes to nearby stars. If scaled up, such technology could potentially accelerate a larger probe to significant fractions of the speed of light, maybe several % over vast distances. These kinds of technologies could potentially achieve speeds of hundreds, maybe thousands of kilometers per second, potentially reducing travel times to the Oort cloud from millennia down to centuries, or maybe even decades for a fast flyby.
So these are the sci-fi level dreams. Is there anything closer to reality?
Well, while these specific breakthrough technologies for dedicated interstellar or Oort cloud missions aren't currently available, one technique that has been demonstrated within our solar system and can achieve extremely high velocities, at least for a brief period during a flyby, is a powered solar gravity assist maneuver. This involves a spacecraft firing its engines at closest approach while passing very, very close to the sun, using the sun's immense gravity well combined with the engine burn to get a massive speed boost, like NASA's Parker Solar Probe is doing, reaching speeds over 190 kilometers per second relative to the sun at perihelion.
Okay, so using the sun for a speed boost.
Right. While this wouldn't necessarily get us to the Oort cloud and allow us to stop or orbit there easily within decades, it could achieve the kind of initial high velocities, several hundred kilometers per second, leaving the inner solar system, that would be a crucial first step toward the speeds needed for these incredibly distant journeys. Concepts combining solar gravity assist with advanced propulsion, like solar electric propulsion, are being actively studied for future missions to the outer solar system and maybe even the interstellar medium beyond.
So we're slowly building the foundations, the concepts for these future journeys, definitely dreaming big. Beyond just the immense challenge of getting there, though, what about the scientific opportunities? Can we realistically enhance our observations from closer to home? Or can we even seriously think about sample return missions from these distant icy bodies, maybe intercepting a long-period comet and bringing a piece of the cosmic dawn back to Earth?
Absolutely. While a dedicated spacecraft mission to orbit or land within the deep Oort cloud remains a very distant, maybe centuries away prospect, our observational capabilities from Earth orbit and the ground continue to improve rapidly, as we discussed. The next generation of telescopes, JWST, with its infrared power, VRO, with its survey speed and depth, will definitely continue to enhance both direct and indirect detection and characterization of Oort cloud objects, especially those in the inner cloud or those perturbed inwards. JWST might, just might, detect the thermal glow of a few large distant objects. VRO will provide an unparalleled statistical census of the inner Oort cloud population. These enhanced observations will absolutely refine our understanding of the cloud's size, structure, population, and maybe even composition without ever having to leave Earth's vicinity.
Okay, so better observations are coming. What about sample return? Is that feasible?
That's arguably one of the most scientifically valuable approaches, and is perhaps more feasible in the near to midterm, maybe within the next few decades, in a direct mission to the Oort cloud. The idea would be to intercept a long-period comet, one confirmed to be on its first trip in from the Oort cloud, as it passes through the inner solar system.
Catch a messenger on its way through.
Exactly. Imagine the fundamental questions we could answer about our solar system's origins, about the primordial materials, about the potential delivery of water and organics to Earth. If we could study a pristine sample of that 4.6 billion-year-old material directly in our labs here on Earth, it would be revolutionary. It would provide ground truth for all the remote sensing and modeling we do.
It sounds amazing, but technically challenging, I assume.
Oh, incredibly challenging. There are significant technical hurdles. First, the orbits of new long-period comets are often discovered only months before they reach perihelion, their closest approach to the sun. They're unpredictable long-term. This makes planning and launching a rendezvous mission extremely difficult. You need fast reaction times.
Hard to plan for.
Very. Second, these comets are moving incredibly fast relative to Earth or a spacecraft when they whip through the inner solar system. So any sample collection would likely have to be done during a very high-velocity flyby, maybe using an aerogel collector like Stardust did, or some other ingenious method to grab particles without destroying them. And finally, the sample return capsule itself would need to survive an extremely high-speed atmospheric entry when it returns to Earth, generating immense heat and deceleration forces, much higher speeds than capsules returning from the Moon or even asteroids.
So tough, but maybe not impossible.
Tough, but perhaps not impossible. Recent advances in spacecraft autonomy, the ability of spacecraft to make decisions and adjust trajectories on their own using AI, might make such rapid response intercept missions more feasible in the future. Allowing a spacecraft to perhaps wait in a parking orbit, identify a target comet, and then autonomously navigate to intercept it and return the sample could be a game changer. We've had successful sample returns from asteroids like Hayabusa 2 and OSIRIS-REx, and even short-period comets, Stardust. Extending that capability to capture pristine material from a true Oort Cloud comet as it passes through is arguably the next great frontier for directly unlocking the Oort Cloud's secrets. It's an incredibly exciting prospect that really combines our deepest scientific curiosities with our most cutting-edge technological ambitions. Hashtag tag out outro.
And so we've journeyed conceptually, at least, to the very edge of our solar system today, exploring this vast, enigmatic realm, the Oort Cloud, a region that seems to fundamentally shape our cosmic neighborhood, yet remains almost entirely beyond our direct observation. It truly represents one of astronomy's most fascinating paradoxes, doesn't it? This invisible giant exerting such a profound influence.
It really does. This immense spherical shell of ancient, frozen, icy objects serves as both this incredible time capsule, preserving the raw materials from the solar system's birth 4.6 billion years ago, and also as an active participant in ongoing planetary processes through the comets it periodically sends our way. And as we've discussed, our understanding of the Oort cloud has evolved so dramatically since Jan Oort's original proposal back in 1950. It's grown from being just a simple theoretical construct to explain long-period comets into this complex, multi-layered structure that we now realize plays crucial roles in solar system dynamics and potentially delivering the ingredients for life via astrobiology, and maybe even influencing Earth's long-term history. It's truly a testament to human ingenuity, I think, that we can deduce so much about a place we've never truly seen just by carefully observing its messengers and simulating its behavior over cosmic time.
So maybe a final thought for you listening today, consider this. If the Oort cloud really does hold the original, pristine blueprint for our solar system, if it preserves the very conditions and perhaps even the raw building blocks of life itself from billions of years ago, what untold cosmic secrets are still waiting out there for us to uncover? What mysteries are locked away in that distant, icy frontier, just waiting for our technology to advance enough, for our observations to get sharp enough, for us to finally decipher those whispers coming from the deep freeze at the edge of everything we know?